Hi, everybody. Just going through 14.1 notes now, changes in matter. 14.1 is chemical reactions. So which is kind of fun. It's a nice chapter to be in class for because we get to do a lot of actual chemical reactions during chapter 14. But it's just a kind of a cool chapter to learn about in general. So we start off today with kind of more of the nuts and bolts of chemical reactions. The central question: what is a chemical reaction, and how do you describe, show what happens during one? Um, and then we have these 5 learning targets. So there's a lot to go on in 14.1. Describe and identify reactants and products. Identify what a precipitate is or when it's formed. Can describe the law of conservation of mass, write out a chemical reaction, and balance a chemical reaction. Balancing chemical reaction, that last one we are going to work more on tomorrow for a worksheet. So we'll do that one separately. I'm not going to talk a lot about how to balance equations in my notes. I'll just talk about the reasons why we need to. So chemical reactions, what are they? So first thing we need to talk about is the difference between chemical changes and physical changes. Physical changes are going to be whenever we're just changing those physical properties, the shape of something, the size of something, things like that. Those are physical properties. How warm something is. If I have water at 30 degrees Celsius or 90 degrees Celsius, it doesn't matter. It's still water, right? I could have liquid water and gas water. That's just a physical change. And when I boil my water, going from liquid to gas is just a physical change because I still have water, right? I still have water vapor, and that's the same thing as water. It's just in a different phase. So that's a physical change versus a chemical change would be like if I put cookies in the oven, I put that cookie dough in the oven and they come out, it's not the same anymore, right? That's a chemical change. Chemical reactions took place to turn that cookie dough into the cookie that I enjoy eating so much. So there are several different things that we can do to kind of that we can look for to indicate a chemical reaction has occurred. The 4 of them that we're going to talk about today specifically. First one is a gas being produced. Okay, so if that gas is produced, that's an indicator that a chemical reaction has happened. Something like that would be putting Mentos in Coke. I watched some videos during this quarantine of some students doing this for like a science experiment, and they would put like 3 Mentos in Coke, and then they would try to like plug it with their face or something like that. And don't try it. They had like Coke coming out of their nose, and I had to laugh every time I watched them. But gas being produced would be an example of a chemical reaction, right? A precipitate forming. A precipitate is one of your vocab words. It's also one of your learning targets. You need to know what a precipitate is. A precipitate happens when you mix 2 clear solutions together, and what you get out is something cloudy. Basically, that indicates a chemical reaction has occurred in a sense that um, when those chemicals, when those compounds rearrange themselves, one of the things that they produced was a solid. Okay? One of them does not dissolve in water. Okay? So typically, like we would do an experiment where we have a blue copper sulfate and a yellow potassium chromate. Those are both solutions, meaning that the compound, a solid, is dissolved in water. When we mix them together, those ions rearrange themselves and we get copper chromate, potassium sulfate, and one of those does not dissolve in water and it turns very cloudy. It's not like we get a solid chunk that's a precipitate. We get like little tiny specks. That's your precipitate. And so when we go from clear liquids to a very cloudy liquid, that's up here. That's a good example that a precipitate has formed and a chemical reaction took place. Next one is energy is released. That could be with heat or with light. Sometimes you mix things together and things heat up, right? That would be an example of a chemical reaction taking place or an indicator that a chemical reaction took place. It does not mean that it did necessarily, but it is a good indicator that this could potentially have been a chemical reaction. And the next one is a color change. Sometimes you mix things together and you mix, and I'm not talking like you mix a yellow and a blue and you get a green. No, that's a mixture. Okay? This is going to be you mix a yellow and a blue and you get a burnt orange rust color. That's like the example I gave you before. Okay. And that type of color change is an example or can be an indicator of a chemical reaction. So in a chemical reaction, we have two sides. We have things going into the reaction and things coming out of the reaction. We can't just put something in and then it just disappears. That doesn't work. What we put in has to come out. Okay, so what we put in is going to be our reactants. Weather's getting nice out now. Hopefully you guys are getting outside. Maybe you have a bonfire every now and then. If you're going to have a bonfire, you need to have wood, and that wood needs oxygen. You're not going to have a fire without oxygen, right? That is what you have to put into the chemical reaction. Okay? Those are what we call the reactants, our starting substances. Products are what we get out. We're not talking like a product isn't ash. That's not what we're talking about. We need to be more specific. If we're talking about oxygen gas and a carbon compound of some type, we're going to be specific about what we get out: CO2 and H2O, carbon dioxide and water. Yes, we actually get liquid water from our fires. Now, here's another example. You can see up above here, H2O, that arrow sign means to produce hydrogen gas and oxygen gas. So water will break down to produce hydrogen gas and oxygen gas. And after that, you notice that we have H2O with a little L in parentheses. That just stands for liquid. H2G means that we have hydrogen gas. And O2 with that little G in parentheses stands for oxygen gas. We also might see S's for solid, or AQ, which means aqueous, and it is dissolved in a solution. Okay, so like if you were to take salt and you stir it around in water and that salt dissolves, that would be aqueous. That would be an NaCl, aqueous sodium chloride. Okay. Now this picture indicates it's a picture of a lab that we would actually do in class, where we are going to look at the reactants that we put into a reaction and the products that we get out. And we want to see, like, okay, are they really different? When I burn wood, it seems as though what I put in just disappears. But that can't be, right? What I put into that reaction has to change. So in this example, we have a closed system. And if we're going to test this idea of law of conservation of mass, what we put in is what we get out, then we need to make sure that we have a closed system to catch everything that we get out. So we have compound B in this little test tube, and compound A is in this bigger Erlenmeyer flask. B is the dark blue, and A is the light blue. And right now they're not mixed, and we put them on the scale, and they have a mass of 200 grams. And that is the entire system, right? Now, we mix it all up, and there's a chemical reaction that occurs, and we know that there's a chemical reaction occurs because it looks like there was a precipitate formed. Okay, it says compound C, precipitate. Okay, so it became cloudy and turned solid, right? That precipitate is our indicator that a chemical reaction occurred. And look at, what did you look at that? The mass remains 200 grams. And that's the truth. Like, that's really the way it works. If we're talking about a campfire, yeah, we burn that wood. We'd have to find a way to collect all of that smoke, all of that ash, everything that we get, the carbon dioxide in the water, and that mass should equal the mass of the wood and the oxygen that we put in. So the law of conservation of mass states that the mass of the products must equal the mass of the reactants. The mass of the products must equal the mass of the reactants. What we put into the equation has to come out of the equation. Now, how are reactions written? So chemical equations, this was your fourth learning target. So a chemical reaction is written using chemical formulas and symbols, and you guys have seen this. I just want to make sure that you guys understand kind of everything that is involved with it. So what we have on the left side of our arrow, the side that the arrow is pointing away from, those are going to be our reactants. Those are what we put into the equation. In this case, it's a methane gas, CH4, and oxygen gas, O2. Okay, so if we have methane and oxygen, we can get a fire. That's going to be a chemical reaction, specifically a combustion reaction. And that arrow means to produce. They react together to produce carbon dioxide and water. So that top example, the middle example I should say, is just pictures. And then on the bottom there is how we actually write that out using the symbols. CH, carbon and hydrogen, and that 4 is a subscript. Notice how we have on that picture, let's see, this picture right here, we have 1 carbon and 1, 2, 3, 4 hydrogens. Over here, O2, well, we have 2 of the same atoms. Over here, we have another red, that's our carbon, right? And then we have 2 oxygens. And over here, we have green was our oxygen, and the yellow were our hydrogens. So you can see how those kind of match up in that chemical equation. The arrow that we use, so for our chemical reaction, this is our total chemical equation, same one that we just looked at. Reactants are what we put in, methane gas and oxygen. The arrow means to produce or to yield, and then what we get out is our products. Reactants react to produce our products. If we were to write that out in words, which is kind of a nice, so, and in what we would normally do in normal class, we would make sure that you're able to write out the reaction using the symbols, like above, CH4 plus O2 gives you CO2 plus H2O, but we also make you write it in words as well. Methane combines with oxygen gas to produce carbon dioxide gas and water vapor. What a fun thing. So now to the balancing part. A balanced chemical equation has the same number of each type of atom on the product side and the reactant side. And that goes back to that conservation of mass. What we put in is what we get out. So if we were to do that, we have to use these numbers that we call coefficients to help balance it. Okay, a coefficient is a whole number that's placed in front of the chemical formula. Okay, when I look here, a CH4, that is a compound, that is methane. I can't change the number of hydrogens, or I can't change the number of carbons in that molecule because that gives me something else. I don't have methane anymore. Okay? So if I know that I have methane reacting with oxygen, I might need to change the amount of methane that I have. Okay? And so I can place a little 2 in front of this. This 2 is the coefficient, and it's like a multiplier. It's like saying I have 2 CH4 molecules. That's 2 C's and then 8 H's. Okay, so how many carbons are represented here in this 2 CH4? Well, I have 1 in my methane molecule, but I have 2 methane molecules, so I have 2 carbons. And then how many hydrogens? Well, 4 times 2 molecules, right? So I end up with 8 hydrogens total. Now, here are some other examples. Like I said, I'm not going to get in a lot into how to balance these equations. I just want to show you why we need to, okay? So one reason why we need to, if you look here, we have a KClO3. Now, it's important to note that each uppercase letter represents a new element. We can't use all lowercase, we can't use all uppercase. This K represents potassium, Cl, that lowercase l means that it goes with the C, so Cl is chlorine and O is oxygen, right? If we look here, potassiums, I have 1 and 1, that's good. Chlorine, 1 on this side and 1 on that side, that's good. But oxygen, I have 3 on this side and 2 on this side. I can't put 3 oxygens in and only get 2 out. That other oxygen has to be somewhere. So what I need to do is I need to balance that equation to try to figure it out. I need to use coefficients. I would end up doing adding a coefficient in front of each of these actually to balance it out. I would have to put a 2 in front of this one, 2 KClO3. That would give me 2 KCl and 3 O2s to balance out those oxygens. And there's many more. You guys are going to definitely practice balancing reactions, but I'm not going to get much more into it in this video. You have more questions to answer for your section review questions for this distance learning day. Thanks, guys.